All right. Good morning, everyone. This is CFRG. We have the second session today. We've got 2 hours, but we've got a really busy agenda, so let's start. And we will start with the discussion on the slides, the last presentation of the Tuesday session about two-lane model for publications. Nick did the presentation, and there were some requests about willing to discuss this. And of course, we are happy to allocate some time for this. So we have 10 minutes, and please, if anyone wants to comment, please do that. While we are waiting, we have minute taker, even 2-minute takers. Thanks a lot to Dan York and Osama. And all other information about the meeting is in the chair slides that were on Tuesday. So is there anyone wanting to comment Nick's slides on the two-lane model, or we can move on?
Yeah, just as a quick reminder for folks who weren't here at the first session, I have a personal draft, which is structured as a BCP, but describes different ways through which primitives can be specified at the IETF in conjunction with the CFRG. And the goal of this is to collect some of the pathways that have worked well and to provide them in a way that allows, whether it's working group chairs or anybody who needs a new cryptographic primitive, a pathway to having the entire IETF adopt and agree on how to use such primitive.
Okay, so we've got 2 people in the queue. Michael, please.
Hi, Michael from NCSC. Nick, thank you for writing this draft. We spoke a bit about this in person, but I had a quick question on forming a dedicated working group point. So I think it's a really good idea to put all the discussion and the bike shedding in one place. I guess it wasn't clear to me that when you have competing requirements or different needs from different working groups, how that's going to work coming from kind of one document from one working group. Could you expand on that a little bit?
Sure. So the idea here is if there's 3 or more working groups who want to adopt a primitive and want to implement them in their protocols, that the advocates for it can come together and hash out and debate what the best parameterizations would be. The goal here is not to have one document that dictates things to different groups, but to have a slate of documents that parallel, that provides code points in parallel for all the protocols that might need it. So, for example, we have LAMPS, and we have the Jose working group, and we have MLS, who are all interested in PQ hybrids, and they're all interested in, have made different choices as to which parameterization to use, which version of MLChem, which version of the elliptic curve. There's good arguments to be made, but these arguments currently are being sort of in silos, where one working group does not see the arguments of other working groups for and against different combinations. So the idea here would be that at the very least, these conversations would happen on the same mailing list, so that it's in the light. So if one group does not have the same people, the same expertise, they would benefit from being in the same room as folks who are looking at implementing this primitive from a different perspective or within a different protocol. That's the idea.
Thank you. Next question, Eric.
So I guess I'd like to just walk through an example, perhaps maybe that would help. So we've had a lot of people who want to adopt, as you say, post-quantum. Forget about the hybrids for a second. It's like the post-quantum algorithms, like, like MLChem specifically, is to some extent a drop-in for Diffie-Hellman, or we wish it were, but we consider pretend it is. People have been pretending it is, even though of course it is not, as you know. And like, what would, it's like NIST standardized, FIPS 203. So like, what happens? And then everyone's like, cool, we want MLChem. What now?
Yeah, let's walk through the flowchart, right? So let's just say it's 3 different groups. They want a chem that's PQ. They think they want MLChem, but it's that's really something that is worth discussing, right? I mean, it doesn't come out of the box that a group would definitely want MLChem. They may want an alternative, but in any case, PQ Chem comes in at the very top of this chart. Is their primitive available, defined by the CFRG or reviewed by the CFRG? And the answer currently is, currently is no. Go to the left. Do other working groups need it? Yes, there's a group of 3 or more groups who are looking for PQ Chems. And this lends you to the form a dedicated working group, in which case they would consult with the CFRG in order to take a look at whether or not this MLChem has security considerations, right? Or the selection of all the different potential groups would come to the CFRG and say, hey, we want to use a PQ Chem. What are the sharp edges for it? And work with the CFRG to produce a security considerations document, much like the MLChem doc that Scott put together. And for all the working groups, there would be registering of code points within this dedicated working group. So you get a TLS code point doc, you get an MLS code point doc, you get a PGP code point doc.
So I think maybe the situation, like, actually, I think, and that's a good illustration. Thank you. So like, from the perspective, as sort of boss is saying in the chat, like, we've already been shoving MLChem and everything, right? And I think you sort of phrased this as having a PQ considerations doc, but like, my sense is that what people actually wanted is to know, is MLChem okay? Now, I think people by and large just assumed that it came out of this process, and so it's basically okay, right? But if it was potentially classic Michaelis, that may, or NTRU, might feel that way, right? And so I guess, like, like, I want to sort of distinguish the question of assessing whether the primitive is good from giving guidance on how to use it. And I'm a little like, I guess I feel like the thing that we definitely need is the second, even if we bypass it in the case where it's been through as an SDO, but external SDO. But like, I think we badly need the capability to say there's interest in using, using NTRU, say in SSH. Is that a practice which CFRG feels comfortable with? Not just like, because I think, like, I guess, like, my sense, if I understand, like, these security consideration documents, is like, that there's the question of, like, what the external box, the external shape of, like, this, of the thing is, right? And there's the question of whether it's internally okay. And like, it could be the case that you could have 2 things with the same external shape, but actually one was perfectly broken, right? And it's not clear to me the security consideration document resolves that question. Maybe you think it does.
Yeah, that's a good question. I think with regard to working groups who want to make the choice of NTRU, for example, off of their own choices, the path would be sort of similar. You'd go, this working group needs a primitive. CFRG hasn't said anything about the primitive, and then it would go down to the other path where this individual will drive either CFRG adopting an analysis of multiple things, or just if that's not on the table, there's not enough interest for comparing comparable PQ things. There, we would potentially get the crypto panel to just review security considerations. And for a if you wanted to use NTRU, part of your security considerations are NTRU's safe for use in this protocol. And so that would be part of the question that would be asked to the crypto panel.
Okay, thank you. I think we are going to have a fair amount more discussion here, but thank you. That helps clarify quite a bit.
Thank you. And Jonathan?
Hi, Jonathan Hoyland. Is the main goal of this to reduce load on CFRG, or is it to just avoid the incoherence of CFRG writing standard track documents, or something else, or both?
The second part is not intentional. That's sort of a consequence of it. The main goal here is to effectively centralize and provide a pathway that's reliable and that can be accountable to timelines for providing primitives in a standards inside of IETF standards. That's the goal. Currently, if you want to introduce some new primitive into your protocol, there's not necessarily an obvious path for how to get that into a whether it's a specification written down or otherwise. And if it's something that hasn't been reviewed by an international open committee, that's even more challenging, right? So the goal is to centralize the conversations so that they're not happening in a lot of different places. Allow working groups to make their own decisions, but also force them to talk to each other so there's less diversity in terms of what people choose.
As a sort of straw man, would it be equivalent or the same if we just said, okay, CFRG is going to meet 4 times each IETF instead of twice each IETF?
I think no. I mean, the danger here is to have an all-encompassing working group that standardizes cryptography, and that'll be a bucket where everybody just throws everything in. I think the point of this is to have focused groups based on primitives and use cases, and have them have strict schedules and end quickly, with HPKE being the first kind of, I guess, the more definitive cross working group example.
Okay, that clears things up. Thank you.
Let's move it to the list, and let's start with our second presentation. The Longfellow. Up here, I've passed slides control to you. Please, you can start.
Hello. Very good. So my name is Abi Shalat, and this is, again, representing a group with Matteo. We've added 2 co-authors to this presentation, Tim and David as well. So let us identify the problem that we're trying to solve here. So there's a desire for zero-knowledge schemes for small identity theorems. So theorems about your digital identity, that's primarily the biggest use case, proving things like age over 18 from a state-issued identity, or other things like my address. Now, there are other solutions to this, like SDJOT, which is another working group has specified here, or the MDOC protocol, which the ISO has specified. But both of those have fundamental privacy problems that prevent them from being deployed at scale. Essentially, those other mechanisms leak information. They, in particular, leak these super cookies, which allow people to track you. Either websites that collude can track you if the scheme is run improperly, or an issuer and a website can essentially track you. The only way to actually solve this properly with all the soundness considerations is to use some sort of zero-knowledge scheme that provably doesn't guarantee, that provably doesn't release anything about the credential, and more importantly, it also doesn't release anything metadata about, for example, the proof. And here, for example, I'll point out that, like the other major scheme for identity credentials, which is called BBS, it's not suitable for these small identity theorems either, because it unfortunately leaks things like the index of the attribute that you're trying to release. So, for example, if you have a BBS credential and some party decides to put age over 18 in slot 1 for Alice and puts it into slot 2 for Bob, even though the proof system is zero knowledge, the proof system does not consider the metadata of the proof, like, for example, which index is revealed, and that breaks unlinkability. So far, the only scheme that works in these applications is a zero knowledge scheme that's fully zero knowledge and that doesn't have any metadata leaks, and that's the Longfellow scheme so far. So the SDJOT people have actually spoken that they have general interest in zero knowledge techniques that are post-quantum secure, and they would be supportive for these type of schemes. So that's one example of a working group that's expressed interest in this type of work. We've had a lot of feedback from EU, from organizations such as Apple and Google, that nobody wants to deploy any new schemes that are based on elliptic curve cryptography. And the preference is to choose post-quantum schemes when efficiency allows. So that said, the whole point of those set of slides is that we believe there is some urgent market need for this type of post-quantum zero-knowledge scheme that's fully zero-knowledge and that works for the type of identity statements that occur in these SDJOT or identity applications that I've mentioned. Okay, so that brings us to the Longfellow scheme. It is one of the oldest recipes for we follow one of the oldest recipes for producing zero knowledge. We can come back to this slide if anybody's interested in how we produce this, but we have two components in it. I want to get into essentially, we've essentially, have a paper about this. It's open source. Again, let me highlight that it's one of the few zero knowledge systems that is practically deployable and that only relies on SHA-256 as a hardness assumption. And so far, we have not found any scheme that fits these criteria that works better in the regime of 10,000 gate circuits to 50 million gate circuits. And that includes the latest work. I'll talk about some of those results recently. What has happened since the last IETF meeting? So that's the main point of this presentation. There's been a second group, this ISRG group, that's completely independently produced a second implementation that is bit compatible with our open source implementation. And also there's been some work with integrating this into wallets and into the European age verification system. Several companies have essentially been able to integrate this into their products. There have been 3 independent security reviews of this, no issues raised with respect to the zero knowledge thing. We've improved the performance, and here I'd like to give a few ideas. So you can, as before, you can prove knowledge of an ECDSA signature. This is used to be a very complex statement, but now we can do this in essentially milliseconds. More interesting though, so for example, the MLDSA 44 signature scheme, we're just about to release a paper on this particular thing, but we have essentially produced a zero knowledge proof of a signature. Sorry, the RS is not correct here, that's a typo, but essentially we have SIG and mu. So essentially, if you look at the verify internal function that's specified in the FIP spec for MLDSA 44, we can essentially prove that we have a SIG and essentially we hold a SIG for essentially a PK and a mu that satisfies that particular function. And this is, I believe, the first zero knowledge proof of possession for a post-quantum lattice signature scheme. And we can do it about 850 milliseconds on like an Apple device. So and we're hoping to reduce that even further. Now, as you can see, it's substantially slower than an ECDSA signature, which is about 16 milliseconds. So it's still about, I don't know, 40 to 50 times slower. But again, MLDSA itself is quite a bit slower than and larger than ECDSA. We also have another example now in our repo. Essentially, it's a post-quantum Bitcoin application. So if notice that Bitcoin, when they publish the address of a particular account, they actually apply a hash function to the elliptic curve point, 2 hash functions, in fact. So in particular, you can harden Bitcoin with Longfellow by giving a proof that you know a secret key such that the RIP of the SHA of the compressed G to the X point is your particular Bitcoin address. And that we can do very, very efficiently, about 87 milliseconds to produce a proof and 60 milliseconds to verify it. And that's also notably 10 to 15 times faster than anybody else is able to do that sort of thing. Okay, I just want to report on one other. There has been a little bit of state-of-the-art work here. Vega is a late 2025 paper that compares to Longfellow. And they use some sort of very cutting-edge techniques, and they claim essentially a factor 2 improvement on the prover time. And so I put that into perspective. Essentially, they require elliptic curve commitments, so they're no longer post-quantum secure. They also don't have a traditional security argument in the sense that they use this technique called folding, which doesn't allow for a traditional polynomial time extraction algorithm for the statements that they have in mind. And so the security guarantees are weaker, and the complexity assumptions are more necessary, and their implementation uses threads, so it's not clear exactly how much faster it is, but their benchmark basically is about twice as fast as Longfellow. And so that's the trade-off, essentially, 500 milliseconds versus 250 milliseconds for essentially the type of proof that we use on the phone. Okay, so that's what I wanted to basically cover. Essentially, that most importantly, we have written a specification of this scheme. It's an old scheme. It uses very old recipe. It's been security reviewed and has essentially a second implementation that's bit compatible, that's roughly of the same performance in a different language in Rust by a totally different group. And so that's the status. That's how far we've come along. And and again, these benchmarks are 2 new benchmarks that show sort of the utility of the thing. So I'll leave it there. I'll leave the last 5 minutes for the questions as per the discussion. If anybody has any questions or comments or feedback on what we should do with this.
Thank you so much. Please, Bess.
Thank you so much for this. You really the hard work is standardization and getting really things to the endpoint, right? It's easy to propose something. So this is great work. So don't. So my question now, don't take it in the wrong way. But I wonder if you could compare it with how this would perform compared to Vol in the Head. I mean, that's the obvious contender.
Yes. So we have some. So the problem with Vol in the Head is that you have to commit to, so the size of the commitment that you have to make with Vol in the Head is related to the size of the Vol, and Vol essentially uses 1 bit or something like that per gate. So even for very small circuits, it's not clear.
So Vol uses 1 bit per witness, not per gate?
Per witness, yeah. So Vol requires, unless you apply a sum check technique like ours, you essentially require 1 witness per gate, per multiplication gate in Vol in the Head. And that essentially is what prevents it from scaling for very large circuits like the ones we're handling. The sum check technique in our work essentially reduces the size of the witness that you need to something very, very close to the input size of the witness, not the circuit size. And Vol in the Head techniques essentially, unless you combine them with sum check, which essentially eliminates the sum check, you essentially need very large fields in order to get the soundness. It's not clear. So I've had several discussions with people who worked on Vol in the Head stuff, but I have not been. I've not found any evidence that it can basically be performant in the same regime. I'm happy to take that up after offline, and I do think now that enough people, I'll create a write-up for why I think that technique can't scale.
Thank you, John.
Yeah, thank you. Yeah, happy to see this. There's a lot of non-privacy use cases for zero knowledge proofs. And I strongly agree with this. It doesn't make sense to deploy anything new quantum vulnerable at this point in time. That's just a waste of resources. So I'm very happy to see this. I like this discussion going on. I would like to see more discussion on what different schemes, what are the performance gains and the properties that you get. So I very welcome this discussion you have with Bas and a follow-up on that, so we can see what is possible.
Yeah, thank you for that. I think I'll follow up with something on the email list with my comments on that.
Thank you. Eric?
Yeah, thank you for the presentation. This is very nice work. I think this is easily fast enough for most applications I'm familiar with, in particular all the age assurance applications. Even if you had to absorb a full second for the age assurance, it really wouldn't be that big a deal. So while it'd be nice to have it fast, it's always nice to have things faster. Like I wouldn't spend a lot of time trying to do that, like except for bragging reasons. As I understand it, this just takes an arbitrary circuit, right? And so I think, for practical applications, of course, we need some mechanism for defining the circuits which we actually intend to prove and verifying they prove the thing they claim to prove, right? And I guess I was interested in your thoughts on how we get to an end-to-end system that is usable in the real world, that makes use of this. Like, for instance, the example you gave of 18, how do we get from the point where we're like, okay, I want eight, what I want to do is prove 18, and I can go read some document that tells me how to do that, and I don't have to figure it out for myself, right? How do you think we and I guess obviously we could just have one where we plugged the 18 parameter in, but you can imagine, well, what if I have to be 18 and I don't know, over 18 under 21 or something more complicated predicates. How do I get a generic system that I can deploy straightforwardly just by reading the documentation?
It's a great question, Eric. So I'll tell you what the status quo is. Of course, you can define some arbitrary complex programming language. What we're doing is working with standards. There is something called DCQL in the OpenID spec that allows you to ask for certain attributes, just the quality of certain attributes. That is the level of the interface that we support. That essentially generically lets you ask for 3 well-defined attributes. And so our circuit essentially does that. It follows the DCQL query format, lets you ask for 3 of the attributes. If you only want 1, you just ask for the same one 3 times. And that's a very good place to start because it's simple enough and it handles many use cases. It does not let you handle arbitrary things like I was born on a Monday, which we can prove, but that's a good starting point for bootstrapping the practical use cases of this.
Thank you.
I agree. And for
Brent,
age assurance, that's plenty good enough. Thank you.
Thank you, Brent.
First, want to say support this work. This is big fan of Longfellow. Minor quibble, calling it ZK lib seems to indicate that it'll have more to do with other things than just Longfellow. So maybe consider naming it something less general. If you're not going to include Vega and BBS and all of the other ZK techniques that people know and love, maybe change that.
Okay, great, thanks.
Thank you so much, Abhi. Tanya, we have already logged the queue, and we are moving on now.
Abhi, you mentioned, is it okay?
The queue was locked before, so sorry. Please take it to the list. So next presentation, an NTRU-based public key encryption, and I am passing you slides control. Please take it. Just a moment, it will work in a moment. Yes, please. Please start.
Okay. Morning, everyone. I'm Yi Jian, and this talk is with Xinhui. We talk about this NTRU-based public encryption. The main question of this talk is, as post-quantum migration becomes real, do we really need a more compact alternative?
It's a mic.
Is it clear? Okay. Okay. So the main question about this talk is, as post-quantum migration becomes real, do we really need a more compact alternative for some like size-sensitive situations. So let's start with some broader context. We know that IML-CAM has been deployed in post-quantum migration, like with some. Okay, thank you. In Web and TLS, Google enabled ML-CAM by defaulting term for TLS 1.3, and also Cloudflare supports hybrid post-quantum key agreement in TLS. Also in cloud services, messaging, they all use ML-CAM in practice. Well, the first message is that the post-quantum migration is not a future topic, and ML-CAM is in progress. And well, in reality, there do exist some minor adjustment, especially for particle fraction and fragments. We use the same example here for the size of ML-CAM. These two are underneath third security and fifth security. And we can see that for ML-CAM 768, they got public key and ciphertext both about exceed 1,000 bytes. And for ML-CAM 1024, they got even exceed 15,000 and 1.5 thousand. By compression, we show that down 1024, which is the latest NTRU-based PKE, it only provides about 1,000 public key and ciphertext. Is about 30 smaller than ML-CAM. Well, what's the packet of size in practice? The first is direct in TLS, clean hello or server hello. It may spell across two packets, and in ARKG v2, ML-CAM can excise the MTU and require extra IP fragments. This is from the previous draft. And why it matters? Since more packets means more tail latency and more loss sensitivity, and higher overhead of the whole communication, especially for some resource constrained links and devices. So this point is not mean we don't mean that ML-CAM is bad. The point is that for some situations, maybe we can look for some more compact alternative. So is there exact solution? Yes, we introduce the NTRU as a natural solution. So we just start a brief introduction why NTRU can be more compact. This is underlying structure. Okay, for ring or module LWE public key encryption, like ML-CAM, it usually requires two ring elements for ciphertext, as we show here, C1 and C2. Where for NTRU public key encryption, it only leads to one ring element in ciphertext. So this doesn't mean it directly cuts the size by half, but it indeed decreases the size by a lot. So NTRU seems good to be a more compact public key encryption. That's a takeaway. The reason is from the underlying structure. Then we take a glance at the development of NTRU. The story begins at 1996, the original NTRU, and this family of NTRU continues to evolve both in practice and theory. They got through some complex construction in recent years, and we see in the original NTRU they got 1860 bytes for the sum of public key and ciphertext, and for the latest NTRU public key encryption done, maybe the size is only 900 amount. Okay, all the data showing this slide is underneath the first security level, and the performance is under AVX2. Okay, this slide we want to talk is NTRU. This family has a long story about 30 years evolution, and it still explores better trade-off between compactness and efficiency, will remain security. Okay, for something may consider. So like MLCAM, the underlying assumption is a module LWE assumption. Well, NTRU, we need some other assumption like an NTRU assumption. So the first concern is that is it safe enough? So we show that there's exists some structural relation between NTRU and LWE still. The left is NTRU, H times F sub G equals 0, and the right is ring LWE, A times S sub E, plus E equals B. Well, the NTRU can be realized as a special ring LWE with 0B. So they do have some relation. NTRU maybe can be seen some realized some ring LWE with a special factor. And for the theoretical hardness, there exists a reduction of NTRU. So NTRU can be reduced to some hard problem like gap SVP on ideal lattices. And this backups the security of NTRU. And for concrete security, there exists some attacks, especially for Taylor for NTRU, like the sublattice attack, but they are on some specific parameter set about larger modules. And for the public encryption context, where VQ is comparable to N, so we needed to consider about that. So the message is that for the public encryption, NTRU has a credible security foundation. We can use it since it along my 30 years history. There's not some large attack can weaken security by a lot. Okay. Then we show some concrete compression of post-quantum CAMs in size, cost, and security, especially for NTRU CAM and MLCAM. We know that for security, we spelled it in 2 columns. The first column is about the security key and plaintext. This is usually the security on the CPA model. And the second column is DFR, namely that's a decryption failure rate. This is about the security under CCA model. Okay, we see here there are several NTRU family CAMs. They show different advantages, such as NTRU HPS, HRSS, and NTRU Prime. They got no decryption failure, and they got higher concrete security level. While the Dawn and Knife, some latest NTRU construction, they show some smaller size and higher efficiency compared to MLCAM. We highlight Dawn and MLCAM as a pair to compare, since Dawn is about the same security as MLCAM, and the size is about 33 smaller, while it's even got a faster efficiency. All the data shown here is still in AVX2, and in standard C implementation, the gap will be larger. Okay, to visualize this, we show a size breakdown in public key and ciphertext. We can see that Dawn is clearly the most compact among the post-quantum CAMs. And this is the cost breakdown. Okay, Dawn, Knife, NTTRU, and MLCAM, they all got high efficiency. Okay, finally, the main question. Do we need an additional NTRU style option for specific deployment? So we need to clarify our position first. So we will Dawn as a size-oriented NTRU family alternative alongside a previous draft about NTRU HPS and HRSS proposed in CFRG. And our target is for some specific situations that are packet budgeted, bandwidth sensitive, and resources constrained deployments. So just one question about is the size, the advantage of size is large enough to justify an additional option. Yeah, since it has been proposed MLCAM and NTRU HPS, HRSS. So we wonder that if the industry or in reality, do we really need a more compact alternative? So we do a warm up about Dawn. Okay, thank you.
Thank you so much. Please, questions, Bas?
Okay, this from a performance angle, this is great. This is a real improvement on MLCAM. But we cannot just adopt this, right? We need to paint a target mark on it and then have analysis for years before we can trust in deployments. And that should start now, right? At the moment, NIST and such, they are focused on signatures. So it's nice to create a parallel thread here if we can. But I mean, this is years away before we can even start trusting this. That's on the process side. Now, on the earlier question, a more direct question is, you define a 512 and a 1024. Is it possible to have a 768 level? Because the 1024 level is not really an improvement. I mean, technically it is, but not really. 512 is clearly an improvement, but if 512 slips, is there a 768 in between?
So you mean for the next 3 circuit level? Okay, that's so for currently Dawn only has a parameter side for of next first secret level and the 5 secret level, but we show here before. Even for the next 5 secure level, Dawn 1024 is still smaller than MLCAM in next third secure level, and is also
yeah, it's smaller, but the difference is not worth it for a migration, right? So the question is there a 768 variant of Dawn possible?
For now, I say it's no. Yeah, it's hard to choose this third secure level parameter of Dawn or some knives such NTRU PKE.
Okay, thanks. John?
Yeah, thank you. I'm very happy to see this focus on key exchange sizes. The main problem with MLChem for very constrained IoT radio is the size of the public key and the ciphertext. Answering your question, if we need this, I think we don't need the original NTRU that has too little advantages. I do think we need this. And I agree with Bas that this needs more evaluation. I hope you will submit this to the Chinese crypto competition. If the Chinese crypto competition includes key exchange with smaller sizes, I think it will have global relevance, not just for China. Thank you.
Yeah.
Thank you, John. Please, Eric.
Thank you for the presentation. I think as you've heard, this probably needs some bake time. I guess the question I was interested in is, are you able to offer an argument that if I liked one of the other variants, I would like this as well, like a reduction to one of these other variants, or am I just stuck analyzing it from scratch?
Sorry, so you mean some reduction?
Yeah.
So you mean the reduction of NTRU, this assumption?
I was saying, for instance, if you could you reduce Dawn down to like classic NTRU or something like that?
Yeah. The Dawn could be reduced to NTRU assumption and the RNW assumption, just like the classical NTRU family. The underlying assumption is still same.
Thank you.
Okay, thank you. Nick, do you have anything to add?
Yeah, the question to the presenter. At the last CFRG meeting, we announced that we're seeking security considerations for different chems. And you listed an individual draft here that was not adopted as something that this could join on to. But my question is, are you willing to write a security considerations draft? Is this part of the plan?
Sure. Yeah, we are willing to write about, especially for NTRU or some lattice chem security document.
Okay, thank you.
Okay.
Thank you so much. And let's move on to the next presentation. Recent advances in FHE. And we haven't got any ongoing work on fully homomorphic encryption in CFRG. And we have questions about this. So we'll be happy to hear a presentation. Please, you can start.
Okay, thank you. Hello, everyone. I'm Xianhui Lu from China. Today, I will introduce some recent advances in fully homomorphic encryption. And I will mainly introduce 3 parts. First, I will introduce very brief history of FAG, and then some progress toward the practical FAG, and finally, the standardization considerations. And first of all, during a very long period of time, the internet mainly focused on the security of communication. But in the last decades or 2 decades and in the future, we need to consider more and more securities in communication. To do this task, the traditional symmetric and public encryption is not powerful enough. We need more powerful primitives. And homomorphic encryption is that kind of new powerful primitives. Given the encryption of M1 to Mn, and the target function can be directly computed on the ciphertext and get a new ciphertext, and the corresponding plaintext is just the plaintext we wanted. That's the definition, that's a very brief definition of FAG. And in fact, FAG is not a new primitive from the history. It was the notation was proposed nearly 48 years before. And in the first 31 years, it remains as one of the biggest open problem in the area of cryptography. And until 2009, the first framework was proposed. And then it took 8 years to design several classical algorithms, such as the BGV, BFV, CKKS, and the CGGI. And now in the last decade or 9 years, the standardization of FAG are considered in several communities, such as the ISO IEC, and many companies publish their open source library for FAG. And on the same time, some practical aspects of FAG are continuing to progressing, such as transiffering and compiling, and today I will focus on. Okay, when mentioned FAG, most of the people may think it is very slow, very expensive. In the early years, this is true. For example, in 2009, the first algorithm of FAG to do 1-bit bootstrapping. Bootstrapping is one of the basic operation in the FAG. To do 1-bit bootstrapping, it takes more than 30 minutes. Now it is much better. For example, if we do a git bootstrapping, it is 400,000 times faster than 2009 record. And the circuit bootstrapping is 100,000 times faster. So nowadays we get much better for the computational performance of FAG. And very similar as the performance of AI, and the performance of FAG also benefits from the progress of hardwares, such as the SIMD instructions. For example, with the help of the AVX instruction, we can get nearly 10 times of speed up for several implementations. And if we use the GPU, and we can get much faster. The recent progress is the ASIC designed by the DARPA project. I remember that the Intel company's chip, it can provide 5,000 times of speed up based on the general implementation in personal computer. Okay, next I will introduce two important topic I think will be interested in the IETF community. The first is transiffering. Transiffering is a technique can transform symmetric key encryption ciphertext to FAG ciphertext. With the help of transiffering, we can make FAG community friendly, which means in the communication or even the storage, we can just use the symmetric encryption. And then when we need to do the computation, and we can translate it to a FHE ciphertext and do the evaluations. In the past decades, the performance of transciphering has speed up very largely. For example, in the 2012, the first transciphering algorithm proposed in 2012, it takes more than 1 week to deal with the 120-bit block of AES. But nowadays, we only need to 14 milliseconds or 11 seconds for different algorithms. It is much faster. The latest is proposed 20 times. And for most of the symmetric encryption used nowadays, for example, the ZDPP use the Snowzook and AES, and the ISO, NIST, and other standards that also have their symmetric standardizations. For most of the algorithms, we test their performance. Many of them takes less than 100 milliseconds, and this also can be speed up by hardware. And the second tool is the homomorphic processor, or we call it the virtual processor, which means to use the homomorphic encryption it is very different from the traditional symmetric encryption. For traditional symmetric encryption, the engineer only needs to know 3 functions: key generation, encryption, and decryption. Then he can use the algorithm very friendly. But for homomorphic encryption, we need to do the very complex evaluations. And even with the help of open source library, it is still hard work to do homomorphic programming. To make this easier, now the solution is we can design a homomorphic assembly instruction set. And based on this instruction set, we can build a virtual processor. And then the engineer will be very easy to use this as the Euro processors to do their development. And nowadays, some of the instructions in the assembly, for example, to add the multiplication, and they must take about 36 milliseconds to 200 milliseconds, and this can also be speed up by hardware. And finally, I want to introduce an example of the application in neural network inferences. For example, in the facial recognition and the speaker verification, in this case, in these scenarios, we only need very simple neural networks. And the performance currently only takes about 0.2 or 0.6 seconds for this light neural networks. And currently, the FHE are already considered in the standardization in ISO, and maybe in the future 1 or 2 years, there will be some ISO standardization for the standard for the FHE algorithms. Okay, finally, the forward path of FHE in IETF. I have 3 questions. The first is, do the internet plus AI need FHE? And I saw in the previous slides, some experts already mentioned this question. And do we need to build a team to discuss the FHE in IETF? And the second is, do we need to prepare some documents of FHE for the research in the CFRG or other groups? Thank you.
Thank you so much. It's a very great topic to discuss now. First of all, we had a presentation on AI versus end-to-end encryption, and this is definitely a connected topic. And we have some questions about the future of FHE in IETF, IRTF, and specifically CFRG. So maybe we'll hear some opinions from the room, but the idea of adopting the topic or discussing whether we want to adopt the topic is very good, very applicable to this. So if you could take it to the list and ask whether CFRG wants to adopt the topic of working on FHE with maybe some ideas of questions which we should reply to. Because when we adopt the topic, first of all, we want to understand what's the intended result of our work. So if some people, for example, Mallory from Tuesday's session, have some requests about FHE or some mechanisms, that will be great. So first of all, we would like to understand what people want from us. And then if we want and we have some questions, then we can try to find the answers. And it's great that you're with us because I'm sure that FHE must be assessed and addressed and sought in CFRG sooner or later. But first of all, we really need to understand what specific tasks should we solve.
Okay.
And I don't think that we have questions from the room. So I really appreciate your presentation. Oh, there's a question from Lee Lan. Lee, please come to the mic. We have a couple of minutes.
Yes, thank you, Dr. Lu, for the presentation. And yes, I don't know if you you have seen or remind. We actually, I and some friends has a hackathon project, specifically for the AI inference and to the FHE. We trying to use the FHE to recognize the pictures such as the cat or the dog, and we see some potentials. So regarding to the documents, I think or the potential works on the IRTF or the IETF, my thinking is I also talk about a little bit with Paul. So my thinking is now we kind of there's a gap we have a protocol gap to process the cipher test in the protocol level. Because when we're thinking about the HTTPS or the IPsec, usually we need to decrypt the payload and to process the entire payload. But when you talk about the FHE, usually we trying to compute directly on the cipher test. Yeah. And how this cipher test can be correctly processed. Maybe we need additional indications for the protocol level. So my thinking is maybe we can do some extensions or the working in the IRTF or IETF to doing it. But we definitely need more time to discussing or think about some of the potential works. So that's my thought.
Okay, thank you so much. And comments from me. We have some comments in the chat. Comments about whether CFRG should or should not do anything with FHE now, provided that we don't have any specific demand from IETF for now, and that maybe some immediate standardization is not possible because FHE is great, but it's very system specific. And that's why we would like to ask you to ask on the list whether there are some demands, requests, desire, because of course we can do some work without IETF demands. CFRG can start research without specific demands, but of course we have our priorities and we want to do the work which is needed for IETF in the midterm, and or if we believe that we understand what specific tasks we should solve. So please take it to the list, and I would like to remind you and your colleagues that in a month we will have nomination call to crypto review panel, and I'm sure that we really need people who have expertise in fully homomorphic encryption and maybe other areas of EHF. So please look at the call for nominations, and if you're ready to do it, please self-nominate if you want. It's to you and all of your colleagues. Thank you so much for the presentation. Thank you.
Thank you.
Let's move on. And this next presentation will be from our remote office. LUMA, low latency, post-quantum, mutual authentication architecture. Xinshu, please start.
Sure. Hi, everyone. Thank you for having me. I'm Xinshu from University of Edinburgh. Mainly work with Michu and Colin. Today, I'm going to talk about LUMA, a low latency post-quantum mutual authentication architecture. That's mainly for the cloud or data center environments. This work has been recently accepted to NDSS, and it's a work that's about authentication design. It could potentially fit into TLS, but we're not here for proposing anything about standardization yet before going to that direction. We would love to, we'd really appreciate any feedback and thoughts on the soundness of the crypto composition in this design. And so that's why we're here, and to get the input from CFRG community. Well, so stepping back a bit, let's talk about why we even look at this.
We don't have sound from the remote room. Nick, could you please check the sound? We can hear you, yes? Please speak again. Please speak. No, we can't hear you. No, still no audio. We see you, but we don't hear you. Sorry, this happens. Let's wait for a moment.
There we go. Testing. All right. There we go. Can you hear us now?
Yes, we hear you.
All right.
Let's
Sorry
begin
about that. It's crumbled.
Yeah, okay, so stepping back a bit, let's take a look about why we even look at this problem.
Okay, ask them more.
Do I need to restart the whole presentation, or can I just continue?
No, just continue, just continue. We heard you before.
Oh, sorry about that. Well, yeah, fast authentication matters in the cloud mainly for two reasons. Firstly, in the cloud, many calls finish very quickly. So most of the time, the crypto operation takes a large part of the end-to-end total communication cost. And secondly, because the cloud uses the high bandwidth fabric, and also it has low latency. So the round trip time in the cloud is very small, like 10 to 15 microseconds, which is different from the internet, where it usually has like tens of milliseconds. And most of the time, sometimes the crypto operation can take longer time than the networking itself. And also, here's how the cloud application look like. And we can see from the figure, the cloud application is built from multiple microservices or serverless functions. And one user request can trigger like multiple internal calls in the cloud. And the microservices are ephemeral instances. They come and go, and they open many new connections very frequently. And each connection requires the authentication. And in the cloud, the mutual authentication is mandatory, where both party requires to do the signing and verification. It doubles the authentication cost, especially compared to the open internet, where only the server is authenticated. And more importantly, the post-quantum migration amplified the PIN. From our experiments, we found that when the post-quantum signature is used, the mutual authentication takes like 50 to 70% of the overall handshake crypto overhead. And this table shows more details we can see compared to ECDSA. The Delirium 2 is like 2.5 slower for the signing, and the FICOM signing is like 9 times slower. There are some work, they are trying to accelerate post-quantum authentication. For example, the KM-TLS, that design, it mainly reduces the authentication bandwidth cost by replacing the post-quantum signature algorithm by the KM operations. For the LUMA, I think the KM-TLS is quite good and helpful for the open internet where round trip time is the dominant latency. The LUMA focuses on this on-pass mutual authentication acceleration. The core idea is very simple. We split the work into 2 parts so we can do the expensive work ahead of time, and we can keep the online operation very fast and light. Next. Yeah, this is quite different from the normal signature workflow. So usually when the message is ready, the signer creates a full signature out of it in the real time, and the verifier validates it with the public key. But we can see this expensive post-quantum signing and verification sits directly on the critical path. And thus, to get the heavy part of the critical path, we introduce to use this online offline signature paradigm. This paradigm allows the sender to pre-generate some keys and prepare for the signing. And it also allows the verifier to prepare for the verification. So during the online phase, they can have the fast signing and fast verification. The important thing here is this paradigm only works when the verifier has the right verification key ahead of time before this connection or before this authentication process starts. It is quite difficult for the open internet where the server and clients are strangers. It's quite hard for them to exchange the crypto state. But for the data center, it is feasible because data center is a constrained network, and the services usually talk to a small and relatively stable set of peers, as we just show in that cloud application figure. Thus, now let's take a look at the construction, how we construction this post-quantum online-offline signature. We mainly consider 2 construction methods. The first one uses this one-time signature online, and the second one uses this trapdoor hash online. And we pick the first one because it only relies on this hash-based primitives, which is widely used in the TLS. So we can make sure that we didn't introduce any new primitives. And this EMG style paradigm allows us to combine the slow post-quantum signature with a fast one-time signature that's performed online. And in our instantiation, we combine the Delirium 2 with Vault Plus. Here's how the Vault Plus works. Basically, the secret keys are some random values, and we do like several times of hashes to get the public key. And also for the signature generation, we also do like different number of hashes to get the signature itself. We choose this Waltz Plus mainly because it has been widely adopted in the practice. For example, both Sphinx Plus and XMSS and adopts this Waltz Plus signature as the leaf elements. And so we think it's sort of widely used, widely studied, and sort of standardized. Yeah. So now let's take a look at how LUMA fits into this TLS 1.3 process. We split the work into two planes. Background plane handles the offline task asynchronously. And for this background plane, we introduced the KDist service for pre-distribute keys. And each endpoint, they pre-generates Vault plus key pairs, upload their public keys to the KDist service, and fetch their peers' public key from KDist service. These keys are organized in batches using the Merkle tree. For the foreground plane, it mainly handles the handshake itself. So the client starts a client hello and advertising that LUMA is supported, and the server deals with the client hello and quickly generates a LUMA signature and sends back to the client, and the client verifies it with the prefetched verification key. Then they do this authentication again in the same fast way, and then once both part has been authenticated, they can start happily chatting with each other. Yeah, now let's take a look at performance. We isolating the verify and signing operation of different signature algorithms. Here, compared to the Lithium 2, we can see LUMA achieves quite fast online signing. That's less than 1 microsecond. And for the online verification, we can do it within 7 microseconds. And this table shows this end-to-end TLS handshake latency. This case is the one client talking to one server. For the MTLS case on the right, and compared to this Lithium 2, we can see LUMA reduces like P50 latency by 34% and P99 latency by 48%. We also tested the concurrency setting where many clients talking to one server. On the left, we can see with the client side loads increases, the LUMA, which is the dark blue one, stays the lowest. And on the right, LUMA sustains the high throughput, showing a good scalability. Yeah, now let's wrap it up. Overall, we found that online offline signature can reduce the post-quantum authentication for significantly, especially for the cloud setting. And we think LUMA is a general approach that can compatible with different post-quantum signature algorithms. And our questions for the CFRG community is we really appreciate any feedback about the soundness of our design, and also is there any like subtle attacks that we may have missing, and we also wonder if there are any better constructions that we should consider. That's all. Thank you.
Thank you. Okay, we have time for one question. Please, Andrei.
Andrei Popov, Microsoft. One thing I would like to clarify, if this scheme relies on a key distribution service, right?
Yes.
Why not just use pre-shared keys with TLS instead of this?
TLS pre-shared key is the different case. We are targeting the first time, the full handshake. TLS pre-shared key is for the reception handshake, which means the client and server, they have to build this TLS connection for the first time, so they know each other, and client and server, they both like save some tickets, and so for the following handshakes, they can use that ticket to do the encrypted communication.
It's possible flow in TLS what you're describing, but there's also an opportunity to pre-share keys using, out-of-band mechanisms, just like in your scheme, and then that, avoids the entire cost of the,
You mean the TLS PS key can be pre-shared with out-band of
externally provisioned PSK? Yes.
why do we need to do that? Because for the TLS resumption, they basically exchange that pre-shared key during the TLS handshake itself.
It's not resumption.
Oh.
You can use a PSK.
It's not resumption. It's externally provisioned PSK. So just a question.
Thank you. Nick, any ideas how to conclude?
Thanks for the presentation. Let's send an email to the list and we can continue the conversation there. Thank you so much.
Thank you so much. Then next presentation, HMAC-based key combiners from multiple keys. Guilin 1, please Guilin, you can start.
Oh, okay. Yeah, thank you. Okay, so here's Guilin. So I'm going to present the HMAC-based key combiner for multiple keys. So we have given a presentation. It is the last IETF meeting at Montreal. It's the second one. This beginning is just basic information about the draft. So basically, we proposed to provably secure key combiner for multiple keys based on HMAC. So called the HKCV1 and HKCV2. So the main features for our construction is that it is a decoupling feature. So it means to generate sort of random master key from multiple of original key, which can be obtained from different methods. We do not need to get the input as the for the public key or for the ciphertext. In that case, it will be more efficient. And the next feature could be that we hope our security proof is more rigorous and more useful. Here I just give a quick look what our scheme looks like. And on the right side, it is a comparison with the currently available existing solutions from standards and from IETF draft. The first one is we call it utilize the concatenation. So in that case, it is useful if multiple keys are available simultaneously. In that case, we can concatenate together and then based on the extract diagram of HMAC to extract the entropy and then try to smooth them. So we use the HMAC twice, such that the randomness can be distributed uniformly for our output key. Finally, we truncate the key to get the length what we need for the pseudo random master key. The second one is in another scenario. So that means maybe the key is available one by one. But during this process, the protocol may need to generate some intermediate keys to protect the following information even before the next key is available. In this case. So we do not give detail here. This part is a comparison about the efficiency and the security, as I just mentioned. The main efficiency is just come from decoupling feature, because in our key combiner, we don't need to require the public key and the ciphertext, especially in the post-quantum key scenario. The public key and also the ciphertext could be very low, not just the secret itself, or maybe the context information, etc. And the security we mentioned here. The first scheme, our first scheme is has better security proof, because it can be approved to be secure just under a little week of assumption, according to the standard assumption for hash function, collision free. It's even weaker than this one. I can base this assumption. But the second one is not that good. It is just proved under the secure under the random oracle. By taking the hash function as an ideal function, we can see this way. And also the similar, the right side is a comparison for the existing schemes. We would like to mention is like the scheme called the NIST SP 800-133. For this scheme, there is some input called the data, but the data is optional. So later we will introduce some new recent result from our team. So we did implement this all of these schemes, 5 or 6 schemes together, and I try to compare what's the concrete performance difference between them. So next I will present the part. Okay, here is the table. There is a lot of numbers. Basically, we gave 2 sets of experimental data. One is we just use the P25 curve, combined with the MLKM for 3 security levels. The main number actually just the percentage part, because from the experiment data we can see the SP133 from the NIST standard is the most efficient one. But as we know, for this scheme, we did not find the formal proof security result for that. If anyone knows the results, please let us know. Then we compare the efficiency of other schemes. Basically, we can say our scheme may be number 2 or number 3 or sometimes number 4. As a comparison, the Cascade KDF from ETSI and also the IETF draft 1 is less efficient. Normally the last 2 schemes here. This is the most important information. Other information are very important. Okay, so here is another one. We just combined with X25519 with the MLKM similar. So the result is still similar. So actually our 2 schemes together with the SP113 can be considered the fastest one. Okay, so here are some short summary. We can say that our scheme maybe 2 of the top 3, according to the efficiency, something a little bit slower than the NIST standard. So the last we have some implementation notes, but maybe I don't mention it too much. We have a dedicated engineer for this part called the Miss Li Xinlei. So we thank you for her contribution. So if you would like to know information, actually you can ask us, or maybe a little later we just send the related information in mailing list. Okay, that's all. Maybe for some questions. Thank you.
Thank you so much. Any comments, questions? Maybe some comment from Nick regarding that current activity with Combiners team. Nick, can you hear me? And we don't hear you. Maybe your mic is off.
Wow, that's it.
I see that your mic is off at the bottom of the screen.
There we go.
Please speak.
Well, we have Deirdre in the queue who can speak more authoritatively on this. Combining things with HMAC as well as with other XOSs, things that have been explored, and there's some recent results on the academic side to prove the usefulness within the PQ context. That's sort of all I can say about this right now.
Thank you.
Go to Scott.
We have some comments from Scott and Deidre. Scott, please.
Yeah, I was just wondering why you're using HMAC as opposed to like Shake. The nice thing about Shake is if you need 137 bytes of output for your whatever, you can squeeze out that much. With HMAC, you have to do this bizarro calendar-based design, which is a pain. I'm just advocating that maybe you should consider Shake. Thank you.
Oh, thank you. Thanks for your suggestion. Maybe we can consider later. Our basic reason we say like the HMAC is just because HMAC is popular in IETF and for the protocol applications. Yeah. Okay. Thank you.
Thank you. Deirdre?
Hi, I just read your draft and I was looking for the paper that has your proofs. It's not publicly available. I don't know if you want to put on ePrint before Springer publishes it as part of InScript or wherever it's being published. Second, it's not very clear from your draft the security properties you're trying to achieve with these constructions. I had to go all the way to the bottom to see what you're trying to achieve, and it seems you are claiming that V2, the extractor is in CCA, but you're not fully claiming the property you're actually trying to achieve there. And then for V1, you claim that is a randomness, secure randomness extractor, not an in CCA combiner or whatever you're trying to achieve. I'm not fully clear what the thing you're trying to achieve with these constructions is from a security property perspective, and also whether you achieve it or whether you're actually claiming to achieve it or not. Clarity there would be most appreciated.
Okay, thanks for your comments. For the security part, yeah, maybe we can discuss it later via email. For the first part, I will update the draft later, and actually paper already published. It's available on the internet. Yeah, thank you. I will let you know. Yeah, thanks.
Thank you so much. Thank you. Now we have Lucas Prebel, hybrid digital signatures with strong forgeability. Okay. And I'm sharing the slides. Yes, please, you can start.
Okay, so hi everyone. I will give an overview and an update of our draft about hybrid digital signatures with strong unforgeability. So it was updated earlier this month. And this work proposes two hybrid constructions, so combining post-quantum and traditional components, aiming at strong unforgeability security. So I will start by recalling the motivation and the problem we try to solve. So first, the usual security model for signature schemes is existential unforgeability, but or EUFCMA, but SUFCMA strong unforgeability is stronger because an adversary who has seen a valid signature cannot produce a different valid one for the same message. And several IETF drafts currently rely on hybrid signature schemes, which only achieve EUFCMA security. However, in several real-world applications, we might need a stronger notion of security, for example, to prevent replay attacks. And so the challenge that this draft tries to solve is how to achieve strong unforgeability, even if one component is only EUFCMA secure. And so in this work, we define two hybrid signature constructions which offer strong unforgeability under different assumptions. And so in the next slide, I will present the two constructions defined in the draft. So the first one is a black box construction, which means the two underlying signature schemes are treated as independent modules. And the idea is quite simple. The hybrid signature is composed of a signature from the traditional signature scheme, the first component, and the second signature is actually a signature not over the message, but the concatenation of the message and the first signature. And so this binding ensures that a valid hybrid signature cannot be modified without breaking the SUFCMA security of the second component algorithm. And so as a result, this hybrid construction remains SUFCMA secure even if the first component is only existentially unforgeable, as long as the second component is SUFCMA secure. However, because of this binding, the signing process is sequential, so you need to first sign traditionally and then sign with your post-quantum component. So this is a difference compared to the composite approach, for example, which can be executed in parallel. And so that was our first construction, and the second construction of the draft is a little bit different. It's a non-black box construction. So it is designed specifically for the case the first component signature scheme is built from the Fiat-Shamir paradigm, and the second component can be any signature scheme. And so this construction is composed of an identification scheme and a signature scheme. And so it is a little bit more compact because the resulting signature is composed of the response from the traditional identification scheme and from the second signature. And but more significantly, the main difference with the first construction is that it's SUFCMA secure as long as any of the component is SUFCMA secure, which wasn't the case of the first construction. For the first construction, the security came from the SUFCMA security of the second component. And similarly, it's the signing process is sequential there. So we implemented those two constructions, and the performance there is not a big difference between the non-black box and black box construction. So the performance shouldn't be a deciding factor between black box and non-black box. The security will be the main motivation for choosing one instead of the other. And in the last update, we mostly updated the security section, so adding some clarifications and speaking about more security properties, and we also clarified and added some editorial modifications. And so the questions that we would like to ask the research group would be if there is any need for these hybrid constructions in real-world applications, if there is any preference between black box and non-black box, and if there is any gap which will need to be filled. And in particular, looking further ahead, we would like to have more people reading the draft and sending us feedback. So thank you very much.
Thank you so much. Please, Scott.
To answer the question about preferences, we have a strong preference for a black box construction. Basically, we don't want anyone opening up MLDSA, inserting some stuff, and hoping they haven't broken anything. Thank you very much.
Okay, thanks for your comment.
Any other comments, questions? Okay, then, if you want someone to share the opinion about this, you can double it on the list, and if people want, they will tell your opinion. Thank you so much. Thank you, Lucas. And now we have a presentation from Emil Lundberg, the ARKG algorithm. Please.
Thank you.
Just a moment. Yes, and I've passed slide control to you.
Thank you. Okay, here. There, thank you. So yeah, I'm here to present a draft called the Asynchronous Remote Key Generation Algorithm, ARKG. I should have noted on the slide that I'm affiliated with Yubico. Also, my co-author, John Bradley, is also here as a remote attendant. So I'll go quite quickly because I don't have a lot of time. In summary, ARKG is a key generation algorithm that enables you to delegate creation of public keys without giving access to the private keys. So for example, you can have some kind of hardware security device which can output a seed, to like a client software, and then this client software can use that seed to derive a key handle and a public key as a pair, without having to do any additional call to the secure hardware. Then you can, for example, use that public key to register something to some kind of certificate authority or something like that. And then when you want to authenticate or sign something, for example, do something with the private key, then you send the key handle back to the hardware device, and then you can do something with the private key on the hardware device. But the interesting part of all this is that this step where you generate key handles and public keys, you can do that any number of times without having to do additional calls to the external hardware. And that's what makes this scheme interesting and useful. So in very brief, how it works, essentially the pairing step at the beginning where one party outputs a seed, it's a exchange of a chem public key and a base private key or base public key for a some kind of public key scheme which supports key blinding. And then when you generate the key handles and public keys, what you do is you blind the public key, and then you encapsulate the blinding factor using the chem. And then that encapsulated chem or encapsulated blinding factor becomes the key handle that you then can send back to the original party, which can decapsulate the blinding factor and then blind the secret key and arrive at a matching pair. So there's some academic background to this. This goes all the way back to 2012 or so. In Bitcoin, where this kind of technique is used to do so-called stealth addresses, that later inspired a proposal from a colleague and myself about how you can use this kind of technique to do backup keys in WebAuthn. At the time, we were not able to find any formal security proofs of this the key generation technique on its own, just the whole of that BIP32 scheme in Bitcoin. So we worked together with a team of researchers, and they were able to develop a formal security proof for this technique. And then later in 2023, at least 3 different papers also proposed post-quantum extensions to this as well. So we have adopted, in this draft, we have adopted the construction by Wilson, because it's a modular construction and has security properties of the original proof. So we have adopted that, and that's what this draft is based on. The other concurrent publications are linked in the draft, but I don't have time to cover them here. So we have some concrete use cases for this. Most notably, or like in general, any case where you have some kind of use for efficient hardware binding in some kind of application where it's useful to have a lot of public keys that are unrelated. So the use case that motivated all this work was EUDI, where the idea was to use this for single-use batch issued keys to not make super cookies out of the public keys. That may not be as relevant anymore with Longfellow, but still, this kind of thing still works. You can use it for backup solutions, as we originally proposed in 2019. And implementation status for this is this will be a tech preview feature in YubiKey 5.8. And we also are working on supporting or using this technique in WW Wallet, which is a UDI pilot, and also Cyrus ID, which is based on that. And right now we're using it to do ECDSA-based credentials, but we're likely to look into using this to integrate with Longfellow later as well, using ARKG to generate ECDSA keys and then layering Longfellow on top of ECDSA is the idea. So yeah, the contributions from this draft is to make a concrete specification or a concrete instantiation of ARKG that's ready to implement as a general purpose key generation primitive. Currently, we define instances for the NIST curves and the X25519 and so, because that's what we're concretely interested in using in practice at the moment. And we adopt this modular construction from Wilson's paper, which is ready for post-quantum instances, and you just, quotation marks, need to define those instances but the framework should work for those. And yeah, I would like to move towards working group adoption of this, if that seems like a good idea. I'm new to this group, so I'm not sure what the process is, but I would like to move in that direction, so this can be a standard they can reference to promote interoperability. And that's my presentation. Please give me your questions.
Thank you, Emil. Any comments, questions? Any support or maybe concerns? Okay, then we can take it to the list if you want, Emil. Thank you so much for presentation, and let's move to the last one. After the presentation from Osama, we'll have some additional announcement from Darja Connolly. And so, Osama, you can start. I'll share your slides.
Do you hear me well?
Yes, we hear you. And I'm sharing your slides now. Yes, and you can take slides control. Please, you can start.
Okay, good. I see the slides. Okay. Yeah, welcome everyone. Thanks for being here. So I'm going to talk about this relay attacks in intra-handshake and proposed solution in post-handshake. I had a couple of links already in the mailing list. So I'm going to talk about first the relay attacks, then give a very quick overview of RFC 9261 and our post-handshake attestation solution, and finally about the formal analysis that we are doing. The work is mainly being done in the seat working group. And why I'm here is basically to make a request to CFRG for recommendations and guidance. What that means is basically we are kind of in ProVerif, we are making perfect assumptions, as is typical with all the symbolic tools. And we want to know if there is anything from cryptographic perspective by making these perfect assumptions that we are missing or could lead to some problems. So that's the main purpose. As I said, I had made a couple of mailing list posts already, one on the relay attacks, the second one on the client handshake traffic secret versus the application traffic secret. And to give you a bit of a context between what this is all about, remote attestation is nothing just a signature from a cryptographic perspective. And these are the three main classes of attestation, how you do signature compared to TLS handshake from a temporal perspective is what is shown here in the diagram. If you do before, that's pre, in between is intra, and after is post. And I'm going to mainly talk about intra in the first part. And as I said, I use ProVerif for the formal analysis. So this is the main question that we have. There are how do I bind that evidence which is signed to the specific connection? So I describe here the three different secrets which are unique to a specific connection. The first one is the Diffie-Hellman secret, GXY. And what that comes from is, from a server perspective, it's getting whatever it got GX from the client hello message, and together with what it had GY for that specific connection. These two things basically make up this secret, and that is what is shared between both client and server. Second one is handshake traffic secret, client handshake traffic secret, and coming from section 7.1 of RFC 8446 basically, and that includes complete client hello and server hello, which means that the first one is completely included in this one, and it's strictly stronger than the first one. The third level is the application traffic secret of the client, which is all the way up to the server finished, which means that again it is strictly stronger than the second one. And the question I have for the research group here is, or what we had in our mind was whether level 2 is sufficient. That's something that came up at the chartering time of the seat working group. And the discussion that basically happened was that whether the level 2 here, I hear a bit of an echo, I don't know where it is coming from. Anyway, the level 2, there are two specific reasons why we think that to answer this question of whether this binding to the client handshake traffic secret is sufficient or not. The first one is that the handshake traffic secret is actually meant to encrypt the handshake messages. And it's irrelevant for the security goals. That's what Ecker proposed at the chartering time of the seat working group. I didn't believe at that point in time. And I was kind of curious about why this is not the case and why this would be not sufficient. And then what I did is, as a follow-up work, was that in ProVerif, I removed all the encryption and of the handshake messages. So everything you see here, KSH, starting from encrypted extensions all the way down up to finished message, KCH encryption. So all messages, I removed all the encryption. Everything stays the same. All the properties are still satisfied as they would be with encryption. It has nothing to do with security goals at all. It is relevant to the privacy goals and not to the security goals. Second point I want to make from our perspective and our study is that servers not yet authenticated at the point in time where we generate that evidence or the signature, just in layman terms, at the certificate message. So that's the only point in time in intra handshake without doing any changes to the handshake protocol. The only way we can put that evidence is an extension to the certificate message shown as 2A. So to do that, I have to have that evidence generated before 2A, and all I can do is just put that handshake traffic secret or some derivative of that or something relevant to that which generates that correlation to do that. And if I do that, server is not yet authenticated at that point in time. As you see, the authentication part just starts from the certificate message. And if I need to put that evidence in there, I have no chance to do any authentication at all for that specific evidence. So with these 2 points, we believe that it's not sufficient, and application traffic secret, as is apparent, it's sending over the real secret that the client wants to send at the end of the protocol. And that's what it really wants to protect. And so our results basically agree with what Ecker said at the charting time. So what we further did to that analysis is to kind of look into all the possible exploration of the intra handshake. That was something which was instructed by the AD, Paul. And what we did is basically took the use case from seat working group, that is the AI agent use case. So basically it's nothing, just a fancy thing that TLS server is acting as the AI agent, nothing different from the protocol design perspective. So wherever you see genuine AI agent, you can just replace it by TLS server. So no technical difference at all. So what happens here is basically if you use the TLS client nonce for the binding, what can happen is the adversary can simply play a relay attack, which is to say that it forwards that or relays that TLS nonce over to the genuine TLS server, generates that evidence and gets it back. And then it relays it over to the verifying relying party, which in this case is the TLS client. So the TLS client accepts that evidence because it's basically coming from a genuine TLS server, and it establishes a connection which it believes is going to the genuine AI agent or the server, but it's not actually, it's actually going to the adversary. So why binding? So the second option, for example, what we have is the server's public key. And that we believe is also insufficient. The reason is that it can be leaked in various ways. One of those is that if there is a vulnerability in the code, and there are a number of those, like we get often these kind of vulnerabilities, there is a lot of evidence already from the practical exploits. And what can happen is basically in such vulnerabilities, or if the provisioning protocol of the key provisioner, the entity which is provisioning that priv ek to the genuine AI agent here, if that entity actually has the key copy of the key, so we cannot actually prove the property that the genuine AI agent is the only entity in the whole world which has access to that key. So this property cannot be proved in that case. And also the provisioning protocol between the provisioner and the genuine AI agent, that can be buggy as well. So there are several of those reasons by which this key can be leaked. And if this key is leaked, as the figure shows, basically the adversary can then get that evidence and certificate from the pipe which is shown here between adversary and genuine AI agent. And using that certificate and evidence, it can then do everything that the genuine AI agent would have done. So that's a single point of failure where if this key leaks, everything breaks down and you lose everything. So whole security argument is based on that, and we reported that attack over to various implementers, and in specifically Coco CI is one of those which actually uses a combination of attestation nonce and server's public key as the binder for the two protocols, the remote attestation and the TLS protocol. And in specifically, like they replicate whatever we propose them, and the attack that we showed them from ProVerif. And just a small rephrasing, there are a bit of nits that we disagree with them, but in essence, basically, they have acknowledged all the attacks. So second part is basically giving you a quick overview of what we propose as the possible solution, or what the cryptographic mechanisms could be for designing a pure secure solution. And to give you a recap of that, there is RFC 9261, which basically what it does is develop a standard handshake for one-way authenticated channel with the server being authenticated by default as per RFC 8446. And what it can do on top is that if server is the attester, the client can send the authenticator request, which is nothing just the copy of the certificate request, which is defined in RFC 8446, but the other way around. So it's the client which generates that message rather than the server. And the authenticator is then generated by the server, which consists of familiar messages, which are the same as the TLS handshake messages, certificate, verify, finished. They are all well analyzed, and they have the nice properties which we can utilize and be happy with it. So what post handshake attestation actually does on top of this is that this has the client certificate request has this certificate request context, and in there we can put that attestation nonce and the certificate as in the TLS protocol handshake message. So it is extensible, and there we can put that evidence, which will then give the way to transport evidence over to the client. So that's the whole functionality that we actually need. So just to give you an overview of what that actually means, client generates attestation request, sends it over, the server generates authenticator that includes the evidence, sends it back, and then client validates that authenticator and appraises that evidence. So the green ones are the changes compared to that. And then I want to come to the final part, which is the ProVerif model, which I have. And the thing that I want to discuss here is specifically if we have missed something from RFC 9261 perspective, or in general from cryptographic perspective. What I specifically want to focus on here is that in 2B, for example, we have the signatures done by the priv EK ephemeral key. And then in 3C at the top, when the TLS protocol, TLS handshake has been established, after the establishment of that, so the signatures in that post handshake certificate verify is done by the priv LTK. That means basically we are ensuring that it terminates within the TEE, and it also belongs to a specific, it also has that specific key which we need. So it provides the proof of possession of both keys. And we believe that this is a secure solution. Of course, this is up for discussion, and we are still working on the formal analysis. And other thing that I want to mention here very quickly is that the two new things, the authenticator request and the authenticator, I will describe the proposals for that. The first one is very easy. For, as I said, the certificate request will be simply the attestation nonce. And then for the authenticator, the three messages, certificate, verify, finished messages. For all of those, you see the equations 2, 4, and 6, which are basically the exporting keying materials. The standard TLS exporters, we make no changes to the key schedule. That's the standard API which is provided. And what we do is basically we invoke those with specific values, meaning that the context label and length is all that we change. And each of them has a different context so that they cannot be mixed and matched. And you also see that 81 and 8hat1 and hat2, which basically means that integrity of all the messages is also protected. So with that, the final idea, basically, as I said, exporters ensure that they are all bound to the connection. Evidence is bound to a fully authenticated server all the way up to server finished. And there is a running hash, as I showed, the hat1 and hat2 coming from RFC 9261. We just invoke those with new labels, but nothing changed. And we use correlation properties in ProVerif to do that. And the question specifically I have for the research group is basically, would you recommend doing a computational proof for this, or do you believe that ProVerif would be good enough for this. For example, like computational proof, meaning the CryptoVerif or the such tools. That's pretty much it. There are some links that you can see afterwards and these references. Thanks very much. I look forward to your feedback or any questions.
Thank you. Osama, we asked you to have some explicit requests for some guidance from CFRG. I saw a couple of questions, but I'm not sure that they were explicit enough. So if you want any guidance on any specific matters, you can ask on the list, or maybe we have anyone willing to comment now, because it's fine to ask CFRG for guidance, but you really have to be very explicit with your questions.
I believe I did have quite a number of specific questions. For example, the one shown on this slide, does the research group believe that it needs a computational proof, is one of those. I had quite a few also, like from places to places. For example, like I can go back here, maybe just in case someone has opinion. One thing which is still like this one is still being debated in the seat working group, but I wonder if someone has any opinion. And I did have like questions like those, whether this is sufficient. If someone disagrees, of course, I would love to hear the ideas of what I have presented. If there is any disagreement, that's what I would love to hear.
Okay, thank you so much. I don't see anyone willing to comment, so please take it to the list if you seek for guidance from CFRG.
Okay.
I don't see anyone willing to comment now. And
Thank you.
as I understand, thank you so much. As I understand, we have any other business from Deirdre. Deirdre, please.
Hi, just a quick announcement. I've uploaded security considerations for MLDSA as a first draft, inspired by talking about other security considerations documents for chems yesterday. It's heavily inspired by Scott Fleur's security considerations for MLChem in discussions with Sophie Schmid. Please take a look.
Oh, thank you. Great.
Yeah, I'd like to add to that is basically if there are other signature schemes that are being actively considered within the IETF, consider to bring this to the CFRG as well. And is the intention, Deirdre, that this could be along the same lines as what was announced on Tuesday, like a set of collections for the CFRG to give recommendations to the IETF regarding
Sure.
which PQ chems to do and how to safely use them?
Sure, just generally, like, for example, FIPS 204 specifies a hash MLDSA variant and regular MLDSA, and talks about things like, well, you can also do external mu, which kind of gives you exactly what hash MLDSA seems to provide on the tin, but none of the caveats. And especially for people who care about using MLDSA in a very FIPS specific way that won't get in their way, about how, yes, you can use external mu in calculating it in a different cryptographic module, exporting it, and then calculating the signature over it in another cryptographic module. Things about sourcing the randomness for signing, for hedged or signing versus deterministic signing, specific things like that, about kind of, here are some choices that are allowed by FIPS 204 and some well-motivated recommendations about what choices to make and why, but also with a clear perspective on, if you like MLDSA, you probably want to be FIPS compatible, not always, but probably, and linking to all the places that FIPS has published guidance to be like, yes, you can do this, it's fine. You might not want to do this, even though it is fine according to NIST, stuff like that. And then if CFRG wants to treat that as sort of like a implicit, like, we like this thing, that's why we're giving you so much information about it, sure, why not?
Okay, yeah, that sounds really valuable, especially if there's ambiguity and options in documents that are published by other SDOs. So this is probably a really good use of the CFRG's time.
Okay, thank you. And now we have to finish our meeting. I would like to repeat that in a couple of weeks, we are going to send an announcement of call for nominations from for a crypto review panel. We'll have a crypto panel rotation, and we really need good candidates there because we've got a lot of work to do. So please, if you want to self-nominate or you want to nominate someone, please do that after we make an announcement. Thanks to everyone for attending the meeting. Have a nice day. Thank you.